In this video, we're going to go through kinetic control and equilibrium. So here we have a reaction profile. On the left-hand side are the reactants. On the right-hand side are the products. So we've been talking about kinetics and thermodynamics. Thermodynamics asks the question, will it occur? And kinetics asks the question, how fast will it occur? Kinetic control occurs between the reactants and the products. When we say something is under kinetic control, thermodynamics predicts a reaction will take place, but if the reaction doesn't occur, we say it's under kinetic control. Kinetic control means that you have a very high activation energy. So in order for the reaction to take place, the bar is set really high. You need a certain threshold of energy that can't be met, or it requires a very high amount of energy to be met. Unfavorable orientations. So in order for the particles to collide, remember you have to have them line up a certain way. So if they're not doing that, those would be unfavorable orientations. And then finally, a high number of particles that must collide simultaneously. So a lot of moving parts, and for them to all line up at the same time, low probability of that happening. So again, we say if you meet one of these conditions, that it's under kinetic control. So it's predicted to occur, but it's not occurring. It's probably because of one of those reasons right there. Okay, so let's look at an example. This is an exothermic reaction. What's the sign for delta S? What's the sign for delta H? Well, it tells us that it is an exothermic reaction. So right away, I know that my delta H is going to be negative. Now, here we are splitting into multiple things. So we're taking AB and it's splitting into more particles. So I have 3 moles on the left side. I have 1, 2, I have, not 3 moles on the left side. We have 2 moles on the left side, and we have 3 moles on the right side. So we're splitting into more things on the right side, more disorder. So our delta S is going to be positive. So the next question is, when will delta G be negative? Always, never, high temperatures, or low temperatures. Well, let's take a look at the equation. Delta G is equal to delta H minus temperature delta S. Okay, so if delta H is negative and delta S is positive, a negative number minus a positive number is going to give you a negative number every single time. So delta G is going to always be negative in this case. Okay, now it says the reaction does not proceed at room temperature. Can you suggest a change to the conditions to make the reaction proceed? Well, it's telling us it doesn't proceed at room temperature, so there must not be enough energy for the reaction to take place. So if we increase the temperature, that will give those particles enough kinetic energy for the reaction to take place. The other thing that we could do is we could use a catalyst. A catalyst is going to lower the amount of activation energy required, and then the reaction may occur at room temperature. Okay, so in our reactions, we are also going to have K values. We'll see these when we get into equilibrium a little bit more here. Okay, so K values come up when we're looking at equilibrium. If K is greater than 1, that shows the products are favored at equilibrium. If K is less than 1, the reactants are favored at equilibrium. So greater than 1, it's the products. Less than 1, it is the reactants. So here is a table of what is considered thermodynamically favorable and unfavorable in terms of delta G and K. So if delta G is less than 0, K is greater than 1, our products are favored, and it is thermodynamically favorable. Thermodynamically unfavorable would mean that delta G is greater than 1. It's a positive, greater than 0, so it'll be a positive value, and K is less than 1. Reactants will be favored. So when products are favored, more products are going to be produced. When the reactants are favored, more reactants are going to be produced. And at equilibrium, both delta G and K are equal to delta G is equal to 0, K is equal to 1, and that would mean at equilibrium that the reactants and products are equally favored. So at equilibrium, they're going to be produced at equal rates. How many times did I just say the word equal? All right, so here are some important equations that we're going to need in terms of delta G and K. So here are the relationships. These are two equations that you can use to convert between them. Now, R is a constant. R will always be 8.314 joules over moles times Kelvin. Your temperature always has to be in Kelvin. Delta G has to have the units of joules per mole, not kilojoules per mole. And K is going to be our constant. It will not have units. So the important things are these three to make sure that you're in the correct units when you're using these equations. Okay, so let's look at another equation here, or sorry, another reaction. It says, given the equilibrium constant at 298 for the following reaction. So our equilibrium constant is here, and we have a reaction. A plus B is going to AB. It says calculate the value for delta G. So delta G is going to be equal to negative RT natural log of K. So we're just plugging in values here. So R is 8.314 joules over moles times Kelvin. 298 Kelvin is going to be our temperature. And then we have natural log of our constant K, which is going to be 1.4 times 10 to the 6th. So if you plug all this into your calculator carefully, you should end up with the value of negative 35.1 kilojoules per mole. And that's essentially it. So we talked about kinetic control, so why a reaction doesn't occur when it's predicted to occur thermodynamically. And then we also went through equilibrium and the K values.